Okay, so thank you very much for the nice invitation to give my talk here in this webinar, which is a very nice thing. So I really like it a lot what I have seen. Now I'm going to talk about something which is a bit different maybe, but I try to make a relation to thermoplasmonic phenomena and hope you will find at least part of it interesting. So I'm going to talk about the origin of the Seebeck coefficient, which was observed in recent years, in the last 8 or 10 years, for ionic conductors. And so I give a very brief introduction to the systems. I talk a little bit about a few plasmonic experiments which have been done. Then I get to a main point, which is with very large Seebeck coefficients of the ionic conductors. So overall, the picture is always what you see here on the first slide. So there is some system, a gel, a liquid, sometimes solid materials, that a lot of things are around. And now you apply a temperature difference, delta T, between the two sides. And what you observe is a potential difference, so which is something and which is due to ions which move within the material. So that is a general picture, and so the relative coefficient between the potential and the temperature difference is a Seebeck coefficient. And I should say, I started to work on these things 8 years ago, 10 years ago, after some discussions with Dan Zhao and Xavier Crispin from Linköping in Sweden. And so there have been quite a few things together in the last years. And so I really have to thank them a lot for their collaboration. Now, okay, so the first experiments of this type were done a long time ago in the 19th century by Nernst. So he's kind of who introduced a lot of things, who set up a few experiments. As you see here, this is an electrolyte solution in 3 parts. This is at low concentration, high concentration. And here you have some boundaries which are only partly permeable. And so you have here, you heat here, and that means you induce electric currents. Because of a higher concentration, the current is stronger in one than the other, and so you find here a thermal potential. So this is one of the first experiments which were done. Now closer to what people do nowadays. So what I really wants to, how these things are described. So the ions in a temperature gradient have a drift velocity. They move. This is due to the second law. It depends on the interaction of the ion with a surrounding, with a solute. And so this makes some local excess energy or heat. And so this heat will flow to the cold. And that is why the ions move in generally to the cold, but not always. This is a usual thing, but not always. And now when you apply this temperature gradient to a material, so the ions move, all of them move towards the cold, but sometimes the cation or the anion moves more rapidly, as here the case for the cation. So the cation accumulates a little bit at the cold side, the anions at the hot side, and then you have to apply Gauss' law, and then you find quite rapidly the potential which you can measure between 2 electrodes, and the corresponding coefficient, which is quite generally given as, so important things are, there is one prefactor, Kb over E, which is kind of a natural quantity. And then here you have the ratio of the difference of its heats of transport. That means this excess heat of a particle in a solvent. Yeah, and so the difference between cations and anions, you divide by kT, and that gives you the Seebeck coefficient. And so Kb over E is a natural thing, because all energies will be of the order of kT when you are at some temperature. And so you expect here something of this order. Yeah, and so this is relevant for colloidal motion in various systems. I give you a very brief, a few experiments which have been done. So, in which kind of show some specific ion effects, for example, here on hot Janus colloids. And so this was done by the Feldman group in Munich a few years ago. And so what they did, so they trapped one of these silica and gold-capped Janus particles in a laser beam. And they observed the vertical position of a particle with respect to the focal plane. In the simplest case, you would expect the particle is trapped in the laser and is attracted to the focal plane and should be here. And so they found that quite generally the particle is above the focal plane. Now, if you suppose that there is some kind of symmetry in the laser beam at the focal plane, so you have vertical forces which are downward, which is the optical forces and the gravity of a particle. And then you have self-propulsion. Janus particles move on their own. And this is now, this would be upwards here because the particle is kept down. And so when you observe this height here, kind of you see the importance of a self-propulsion. And so what Feldman and colleagues have done, so they have measured this height as a function of a laser power, and that for different salt solutions. And here are just 3 of these solutions, and I give a result I found. This jump here I won't discuss, which is due to the complexity of a laser beam. And so you see that the height you measure is different for the 3 different salts I have used: sodium chloride, lithium chloride, and sodium hydroxide. And now we see, and this here, in fact, what this means, the Seebeck coefficients of these particles, of these electrolytes are well known. And so what you see, at least qualitatively, the sequence here, so the sodium chloride, lithium chloride, and sodium hydroxide, that follows, in fact, these values of the Seebeck coefficient. Now, so really, why does one observe this difference? So this is just when you look at such a particle which is heated by the laser. So there is an excess temperature, so it is hotter than the surroundings, and then you have some thermocharge accumulating on the particle. So this is now a hot surface which you have seen before in a 1D geometry, which is now spherical geometry. The hot surface is a particle surface. The cold surface is a vessel, so which is far away at infinity if you want. Now you accumulate here some surface charge, which is of the order of a few hundreds of elementary charges. And because it's hotter here on the cold side, on the silica side, that means you have a dipolar moment. This dipolar moment induces an electric field, a dipolar field. And this field now along the particle creates electrophoretic motion. So this is something which has been observed in various situations. And so you have a particle which is now moving. And there is so one can also just look at the monopole term of an electric field. So this is a colloidal particle or a gold particle, if you want, in an electrolyte. If you heat the particle, you accumulate here this charge, which is given by the Seebeck coefficient, the excess temperature, and by various parameters of the size of a particle, and which can be a few hundred of charges up to 1,000 charges. So I think this is the only possibility to, at least as far as I know, to create unscreened electric fields in an electrolyte solution. So you have an unscreened electric field with monopole field. So the electric field goes as 1 over r squared. And I think there is no other possibility to create such strong electric fields up to 10 kilovolts per meter at the particle surface. Yeah, just to give you an idea, so what this Seebeck coefficient means in electrolytes and how it can be used. And yeah, there is another experiment I want to show by Yuebing Zheng from Austin in Texas. They have looked, it's kind of a similar thing as you have just seen. So they heat here a gold surface, which a boundary of an electrolyte solution, and you heat locally here. That means you accumulate charges here, which are chlorine ions. The corresponding CTA ions, they form micelles, are in a bulk, and so you have an electric field which points inward towards this hotspot here. Now you have again colloidal particles, which are which are positively charged because the CTA ions absorb on the surface, and so you can easily trap with very low laser power, less than 0.4 milliwatts per micrometer squared here. So you can trap these particles here at any positions, and you can play around, and you can kind of molecules with these particles. You can do a lot of different things. So that was just again to show you a few applications in these plasmonic systems. Now I'd like just to say 2 words quite generally on thermoelectric performance parameters. So people have used a lot, so electronic materials for a long time. Now in recent years, we have looked at ionic systems. What is always kind of, there are 2 parameters. Now as for particle trapping, as you see now, or for sensing applications, when you want to detect temperature differences, for example. So when you have to look at the Seebeck coefficient, if you look at power applications, so harvesting of waste energy or cooling. So there is a figure of merit, which depends on a square of a Seebeck coefficient, the electrical conductivity divided by the thermal conductivity of your sample. So this is just in general what you have to look at. I'm going to talk only about the Seebeck coefficient. And now I come to the systems which have gained a lot of interest in the last 8 or 10 years. So this is a map of all kinds of ferroelectric systems. Here you have a Seebeck coefficient in millivolt per Kelvin, and that is for electric conductivity. You see the conductivity varies about 12 orders of magnitude, the Seebeck coefficient about 3 orders of magnitude. And here to the right, so down at the bottom, so high conductivity and small Seebeck coefficient are all the metals one knows. Here, 100 times smaller conductivity. These are common solid-state semiconductors. Yeah, and here one has organic semiconductors, which are typically conducting polymers. And now here the green area, that is now the thermo-ionic materials, which are quite recently observed. And what you see immediately, the Seebeck coefficients here are about 100 times larger as you find for most conductors, and 1,000 times larger than what one finds for metals. And again, I say this is kind of its natural unit, kb over E, which is 85 microvolts per Kelvin. I'm going to show this a bit in more detail. So a little list on things which have been done. So in any conductor, you may say you have negative and positive carriers. In electronic systems, it's electrons and holes, which just means electronic states below or above the Fermi surface. I call them electrons and holes by symmetry. And so for metals, we said the Seebeck coefficient is very small. This has been rationalized by Mott in '69 by what is now called Mott's formula, and which one understands directly why the Seebeck coefficient is so small. To a large extent, the contribution of holes and electrons cancel each other, and so that's why it's very close to very small, and in 2 dimensions it's even 0. In semiconductors, so you get bigger values due to some band engineering and doping. And so the largest value here, the 20 kb over E, have been observed for organic semiconductors, so for this conducting polymers. Salt solutions, as I have shown you a little bit, are also of the order of kb over E. And now, in the last 8 years now, a lot of people observed very, very much higher values for various systems, so very simple and cheap systems, as here this potassium chloride solved in gelatin, or here sodium hydroxide put in this ordinary polymer PEG, polyelectrolyl glycol. Or here this is a polyelectrolyte matrix, PSSR, so polysulfonate, polystyrene sulfonate with sodium, with some water. This is very ordinary cellulose, which is obtained from a wood. And again, you just put highly concentrated sodium hydroxide. And here, once you see, you have values of 100 or even 300, 320 kb over E. And all these, at first sight, all these materials don't have much in common. So except that you have always some polymer ion or just ionic, so ion conducting. The conductivity is usually quite low, but these very big Seebeck coefficients. Now there is no way of understanding that in the pictures one usually had for the electronic systems or for salts. And so I tried to give you a few ideas where these very big values come from, and so what we found out on this during the last years. Now, the first important thing to see is that these systems, so the conductivity occurs through hopping dynamics. So quite generally, so the enthalpy landscape or free enthalpy landscape of an ion will be something like this. And so this is a three-dimensional network. And so there is always some minimum resistance way of path through the system. And that means one can easily just replace this by a periodic potential. And this is a model I'm going to show and to use. So a kind of periodic potential, which is the typical height of a Berry height, is given by the distribution of a Berry heights here. And there is a hopping rate, which has a gamma, which has a prefactor gamma naught, and some activation free enthalpy. So there is enthalpy term and an entropy term. So this is the usual picture one has. And for a lot of these systems, that has been confirmed by conductivity measurements. When you look at the temperature dependence, you see that. Now, what happens if you put this system in a temperature gradient? And now there are two. So, and when we look for a Seebeck coefficient, that means you look for some kind of drift velocity of the ions, and that means some jump rectification. That is kind of one looks at here. And now there are two main quantities in the rate, must come kind of from a rate distribution. So there is a temperature. So first you change the temperature, and so in fact there is a ratchet mechanism. When you look at two nearby wells, the temperature is not exactly the same, and so what you see immediately, this rate, it's slightly bigger from the hot to the cold side than in the other way around. And the second thing you can have is some kind of a skew potential, so a washboard potential, where the minimum enthalpy kind of varies through the system. So maybe it's lower or higher in the cold side, but we don't know. So anyhow, we suppose that here there is a slope, a finite slope of this bottom of the wells. Yeah. And so first I'm going to show you to work out a bit more the ratchet mechanism. Now, the ratchet mechanism, one looks for the drift velocity, and it's easily just simply given by velocity is given by the distance between two wells multiplied by the difference of rates for forward and backward jumps. And as I just said, so the temperature difference is very, very small. So you may just so expand the rate in powers of this small temperature difference, and you find this expression, which has a very nice shape, and so which is proportional, which is negative. So it means the drift velocity is always to the cold, which has here the enthalpy, the activation enthalpy of a barrier. So here the barrier height, yeah, divided by kT. And since barrier heights very often they are much higher than kT, that means you get here a factor which is much higher than, which may be higher than kT. And now, if one looks at the steady state with ions and cations and anions, one easily obtains the Seebeck coefficient. So one has to suppose that the system is neutral in the bulk, and there are possibly positive and negative surface charges. And one finds readily the Seebeck coefficient, which is again given by this prefactor Kb over here I talked about, and then by the enthalpy barrier of cations and anions, and by the density, so the concentrations of cations and anions. In many systems, this is the same. When all these additional factors just 1 over 2, so kind of they disappear, but they may also be different from each other. Sometimes one has the mobile ions may not necessarily have the same number for both charges. Yeah. Now, I'd like to show one system, which is a particularly simple system, an ionic liquid, which is a bit a toy ionic liquid, which have a lot of experiments have been done on this. All its properties are well known. So with TFSI, cations and anions are big ions, so big molecules, and there is no solvent. So it's only these two ions of molecular weight about 150 for the cation and 250 for the anion. And now the Seebeck coefficient measured for this system is minus 0.85 millivolts per Kelvin, which corresponds to about 10 kb over E. And this is a nice thing, so because for this system, as I said, everything has been measured, and so it's easy to do. This is a theoretical formula I have shown you before, and now here the charge carrier concentrations and the enthalpies are measured. The enthalpies are 270 and 260 electron volts for cations and anions. And now this ionic liquid, it's well known for years, has a particularity that the cationic carriers are much fewer, much less than the anions. This is probably, so the picture people have of this is due to a fact that the cations kind of aggregate. And so if you look at the diffusion coefficient of anions and cations, you find that the cations diffuse a bit more faster, by 50%. So the diffusion coefficient of a single cations are faster than of anions. However, most of the cations are in some aggregates and don't move, and you find that the conductivity is largely determined by the anions, and so is the Seebeck coefficient. And so you easily find from these numbers, you find these values, which is very close to the experimental value, and so which strongly kind of supports the idea that this ratchet mechanism and so this hopping thing is really related to what people observe for these systems. Yeah, so now I come to the second. So this can explain now, this can explain Seebeck coefficients up to 20 or 30 or 50 maybe kb over E, but it cannot explain 300 if you have such a high Seebeck coefficient, such a high barrier height. So in fact, you have no conductivity anymore. And so this cannot be the whole thing, the whole story for the complex systems I have shown you also. This is a very simple system, a two-component system only. There is no other molecular or other component in there. Now, now to understand or to have a rational for these much higher values in these more complex systems. So we started from the idea that you have the minima of a wells, so depend on temperature, and you go through the system, so you may uphill or downhill depending on the sign. Now there is a trivial dependence which is just due to the temperature. This is very small, which is known, which doesn't help, so which does not really explain the thing. So what we came up with is so to look at some free enthalpy of a charge carriers. So they depend directly on temperature, and then they depend on a molecular component, on the concentration of some component, and just think of water. It can be different things. It can be more complex things. It can be mixing ratios or things. But anyhow, there is some think of water concentration, which is certainly depend on temperature, and which may give a much stronger dependence on these bottoms of our wells than the simple temperature dependence. And this right now is G plus G, and this is now the derivative with respect to the concentration, and then this concentration. Yeah, and then again you can easily work out the Seebeck coefficient, and then what one finds, the Seebeck coefficient now takes such a form, the additional term, so you have that from a ratchet effect you have seen before. And then there is a second contribution, which is now the derivatives of the enthalpy at the bottom of a well with respect to some water concentration of cations and anions, again the difference, and this is now the non-uniform concentration of the water or this molecular component due to the temperature. So this is kind of a picture when it's come up from it, which just gives a rise to such a Seebeck coefficient. And now there are some indications for this. There are quite a few systems. It's well known a few systems absorb a lot of water, and so here I come directly to so I still have 5 or 8 minutes, haven't I? Yeah. Yeah, so I come directly here to
a bit more than 5 minutes.
Okay, so
almost 8.
I come directly to what we found out. So yeah, so this is you have seen the experiment. So it's very complex systems. Very often people don't really know the structure is usually not known. Even sometimes people don't know exactly what it really looks like, what goes together. For example, quite often the hydroxide ions, they kind of bind to other molecules, which is not very well known. However, so now my colleagues in Linköping, so Dan Zhao and Xavier Crispin, they did very nice experiments recently. So we tried to understand now the role of his water content. So this is the simplest thing to do. And so we looked at a polyacrylate anion with sodium or with potassium with some water. And so now when you do the experiment now, you have seen before, with the sample is open, open to air. So one measures Seebeck coefficients of 140 and 375 kb/E. So this is the biggest value I think which was found so far. And now you do the same experiment, but you seal the sample. So that means the sample does not interact with air. In fact, then one finds much smaller values of 20 and 17, so much smaller for these two things. And the only reason is that there is water in this sample, and if you heat here on this side, the air sample interface is hotter than here, and so that means the equilibrium of water absorption will be different, and so in fact you change the water which is absorbed on the hot side and on the cold side. And so to make this even clearer, so what they did then, so we discussed this for quite some time. So what they did then, so they just made so this is now the explanation here. Yeah, so this is the explanation. So you see, so this is done at relative humidity of 38%, and so the open sample you just see. So that's the idea that you have here few water, so the water is dissolving here, and so that means a much drier system here than there. And now across this that may enhance the water gradient in your sample along the temperature gradient. There is in a sealed sample, which is not the case, there may be a slight contribution of water, so the water will distribute within the sample, but the effect will be much smaller than here. The problem is now here you can you can check and work out things. here now, so this is a formula you have seen before. And now here, the second term now, so the concentration dependent term now takes a very different form. So that means you have here the constant, so you have mu. Mu is a chemical potential of a water vapor in air, so up here. And what you have to look at, how does the concentration in the sample depend on vary with the chemical potential outside, and the outside chemical potential is also depends on temperature, because air here is colder than here, so you have outside also the same gradient, and so you have to know the gradient of the temperature derivative of a chemical potential in air, which is also not so easy because you know, you have to, yeah. And so basically an experiment which is much clearer. So what we did then, so again, there is such a sample at relative humidity and then sometimes temperature, and now you wait for some time, so the sample absorbs water to some degree, so it's a continuous, a constant water concentration within the sample, and then one heats the sample to another temperature. So here T is T0 plus delta T, but it's a uniform temperature throughout the sample. So there is no proper Seebeck effect, in fact. But what happens now, water is dissolving here from the surface, and now you get a concentration gradient through the sample, and now you just measure here this potential difference, and again you get these very, very big values that is now expressed really of a potential. So here 120 millivolt, which is really very important just to have some chemical change within a system, and to have a potential difference of 120 millivolts. So it's quite a lot. And what you see now, when you heat to different temperatures, so here it's so here this is now at as the temperature T, so as a final temperature, you start from the same T naught, and that means you dissolve more or less water, and now you see here that this potential difference depends a lot on this temperature. And so again, that just shows you that it's a very, very strong so chemoelectric voltage, if you want, so a voltage difference due to a different water contribution. Because as I say, here the whole sample is on the same temperature, and so there is no proper Seebeck effect. Yeah. So this is, I think I wanted to show. My time is over, so I guess I stop here, and thank you very much for your attention.
Thank you, Professor Würger. I definitely very surprising observations, but now we start to understand what is going on. If there are no immediate questions, I can start with one. I was noticing that many of the systems in which you have this giant or very large Seebeck effect are polymeric. So I was wondering whether people have studied the influence of the molecular weight of the polymer in the context of your explanation. Can one say that in fact, you know, if you have this polymer, it's a very high viscosity or maybe solid-like system, so that there is no, you know, in a more less viscous system, there would be a transport of, I mean, the concentration gradient wouldn't be that large because of transport through the
there is quite a
viscosity. So, you know, anyway, is there a connection between the polymeric nature and the transport coefficient?
Yeah, so there is. So the Seebeck coefficient, you want to say. For conductivity, any other conductivity is quite a strong dependence. Now, first I should say, so the conductivity in this system here, for example, it's only due to the potassium. So this is quite a big polyelectrolyte, so it's an amorphous system, so it's a solid kind of, yeah. So it,
I could imagine that the conductivity of potassium is much higher in a low viscosity system, like an ionic liquid or a solution in a water solution, where ions move easily, than in a polymeric system where you have a lot of entanglements. And so that's a little bit your argument about the redshift potential, right?
No, but
is that connected?
It's very, very general. This is really just that I should have explained that movement. So the redshift, this is really something different. Where is it? Oh, here it was. Here, this is really something very general. So this is very general. This is just that. In fact, when you say what does a jump mean? So here is it really what does a jump mean? Jumping over a barrier. It means there is here an energy fluctuation. so at some temperature, and your particle takes up this energy of a fluctuation, gets over the barrier, gets down on the other side, and releases the energy on the other side. That means this is really the energy, the enthalpy of transport, because really take this enthalpy, delta H, at least essentially this enthalpy, to the other side. And so this is very general from the second law. It kind of tells you very, very generally.
Yeah, sure, but what is the difference between these potentials when you go from a normal liquid, let's say a simple liquid like an ionic liquid, and a polymer system, a polyelectrolyte? Is the potential really different?
You want to say the barrier height?
Yes, I don't know. I'm speculating that this effect is observed. So whatever the origin is, the effect is observed essentially in polymeric systems.
So in polymeric systems, so this is not really polymeric, for example.
No, exactly. But also you have
in a polymeric system. So just the last thing I have shown you this year, for example. So when we have looked quite a few different molecular weights of the polyacrylate here. Yeah. Mm-hmm. And so you see that now the conductivity goes down if you have longer molecules. Yeah, not very strongly, but it goes down. Whereas a Seebeck coefficient has a strange behavior. It first goes up and then goes down. We don't understand why, but this is certainly much more complicated. The Seebeck coefficient, or this potential here, in fact, is the ratio of two transport coefficient. In itself, it's not a transport coefficient, it's a ratio of two. And so a lot of, in many cases, one would expect the viscosity, for example, to drop out of this expression.
Yeah. But you would expect, the same gradient, the same role of water could be expected also in a normal liquid, right? If you evaporate water on one side, you would expect. So something makes the polymeric system more sensitive to this water concentration gradient than the normal liquid. So is that due to a higher viscosity, for example?
So I think the large Seebeck coefficient has not to do with viscosity. It does not depend on viscosity. It's really the point where, so since you have to jump over a barrier, you have to take this whole energy, so a barrier height, over the barrier. Because a particle takes up its energy on one side and releases it on the other side. And that is kind of a point. So this is really the heat of transport, which is, and this is kind of at the origin. So as tells you the formula, it's proportional to delta H. For an ion in water, all the energies a particle carries, all the interactions are just kT. That's why they are much smaller. Yeah.
But I feel that we are moving to the discussion part, so I have to stop. So I look for other possible questions or remarks or comments from other attendants. Maybe in the chat. Don't hesitate to speak up if you.
I would ask something
Frank,
maybe in the same direction. So as I understand, what you call the ratchet model is just a normal thermal drift of the ions, just with a barrier in between.
Yeah.
So you have a rough potential energy landscape. But so is that really? I mean, for me, this is not a ratchet, because a ratchet is something where I have fluctuations and I switch a potential. And
if you don't want ratchet, so
okay,
it's a rectification. You may have a skew barrier, or you may have a barrier. Different. I think people call a lot this model a lot ratchet model. It's not of so it's
But okay, it's then I understand it right. It's a thermal drift in a rough, large potential barrier. So, okay, thanks.
It's rectification of jumps because of a thermal gradient. Yeah.
All right, I don't see or hear any more comments. So I propose that we switch to the general discussion. So please, don't hesitate to speak up and ask questions to any of our three speakers, as far as they are still present.
Maybe I can add to that, Alois. So does that mean you have solved the Kramer's problem with two different temperatures on both sides, where the shape of the potential also plays a role with curvatures?
No. This is no. This is no. I've not solved the Kramer. Certainly not. I don't say that. No. In fact, this was so in itself this ratchet motion, if you want, it's known. It has been known from the 60s. I discovered that due to a referee remark. So from the 60s for vacancies in gold and silver. So you have gold and silver crystals, and you have vacancies. There is an atom missing, and this missing atom, these vacancies, may diffuse. And in fact, the diffusion of these vacancies is exactly the same law, for example. Yeah, with much higher variance. And so this has been, I think it was in the 60s and 70s, one of the big things for this metal crystal research and so on.
Okay.
It's not nothing so not very fundamental, but it's an effect which exists.